Good morning, students. Today we are discussing Chatlier's principle. Okay. There are some important factors which affects the equilibrium state of a reversible reaction. Like first one, change in concentration of reactants or products. Change in concentration. Then second one, change in temperature of the system. Change in temperature of the system and change in pressure. Also catalyst, presence of catalyst, also the equilibrium state is affected. Okay, so the reaction, due to this, the reaction will takes place in some direction to reduce this effect, okay, and to reach the equilibrium. This was clearly explained by Chatlier's principle. So Chatlier's principle states that Chatlier's principle states that if a system in equilibrium is subjected to change in concentration, pressure or temperature, okay, what happens? The equilibrium shifts in the direction that tends to reduce or to counteract the effect of the change. Okay, so if a system at equilibrium is subjected to change in concentration, temperature or pressure, the equilibrium shifts in the direction to reduce or to counteract the effect of change. Okay, this is the principle stated by Chatlier. Okay, so now let us explain one by one. First one, effect of change in concentration. First one, effect of change in concentration. Effect of change in concentration. When the concentration of one of the substances of the system at equilibrium is increased, that is either reactant or product, its concentration is increased, then equilibrium will shift in the direction which decreases the concentration of that substance. Okay, so first case, if concentration of reactant is increased, if concentration of reactant is increased, what happens? The reaction will shift in the forward direction. Okay, so in order to reduce the concentration, the reaction will shift in the forward direction and more products are obtained. The reaction will shift in the forward direction and more products are obtained. Now, second case, if concentration of product is increased, then the reaction will shift in the backward direction in order to reduce the concentration of the product. Okay, and more reactants are formed. Okay, if concentration of products are increased. Then reaction will shift in the backward direction. Okay, backward direction, and more reactants are formed. Now, if any of the substance, any of the species in the solid state, then its addition does not alter the equilibrium. Okay, now let us take one example. Some ferric salt is taken, ferric salt solution plus thiocyanate solution gives FeSCl. Complex ion is obtained. Okay, so this is pale yellow in color. This is colorless. Deep red. Okay, so first we are adding some ferric salt containing Fe3 plus ions. So we are adding this reactant. So the concentration of this ferric salt increases. So what happens? In order to reduce this concentration, forward reaction favors and more products are obtained. So after some time we can see that the color of the solution deepens. This shows that more complex ions are formed, and due to this red color deepens. This is one of the example. Okay. Second factor, effect of change of temperature. Effect of change of temperature. So, increase or decrease in temperature also affects the equilibrium. So, according to this principle, if the temperature of the system is increased, if the temperature of the system at equilibrium is increased, what happens? Equilibrium will shift in the direction in which heat is absorbed. Okay, in which heat is absorbed. Now, first case, increasing temperature will shift the equilibrium in the direction of endothermic reaction. So, the direction in which heat is absorbed. So, endothermic reaction, the heat is absorbed. So, first case, increasing temperature shifts the reaction in the direction of endothermic reaction. Okay. Now, what happens is decreasing temperature. Decreasing temperature shifts the equilibrium in the direction of exothermic reaction. Okay, shifts the equilibrium in the direction of exothermic reaction. Exothermic reaction. Now, let us take one example, that is Haber's process, manufacture of ammonia. Example, manufacture of ammonia, that is N2 gas plus 3H2 gives 2NH3. Forward reaction is exothermic because delta H is equal to energy is released minus 92.4 kilojoule. Okay, so backward reaction is endothermic. So what happens? Here forward reaction is exothermic and backward reaction is endothermic. So if we increase the temperature, what happens? The endothermic reaction favors. So backward reaction favors. Okay. So what happens if we decrease the temperature? The reaction, the equilibrium will shift in the forward direction. So in order to get better yield, what we have to do in order to get better yield? That is, more products are obtained. For that, we have to decrease the temperature. Decrease the temperature, then only the forward reaction favors. Okay, so more products are obtained. Okay, this is an important factor. Now let us take another example. So normally at an optimum temperature of 773 Kelvin, the reaction is taking place. At this temperature, we can increase, we will get the maximum yield of ammonia. Okay. Now, another example, N2 plus O2 gas gives 2NO. In this reaction, forward reaction is endothermic and backward reaction is exothermic. Because energy is absorbed during this process, 180 kilojoule. This much energy is absorbed. So forward reaction is endothermic, backward reaction is exothermic. So in this case, to get better, what we have to do? We have to increase the temperature. Increase the temperature, we will get better yield. Okay, so these are some of the examples.